All right, everybody, we have a request to do part 4, fall 19, test 3. And let's try to find where it's open here. Fall 19, test 3, part 4, question number 1. And we should verify the audio is working, and it is. All right. We're starting off with what kind of reaction? KH. KH has a spectator, an anion, and it's a strong base. Yes, it's an acid-base reaction. Take one of the H's off, top or bottom, doesn't matter which one. Make sure you put a lone pair on the carbon that you take the H off. You will get C-triple-C, lone pair, minus. Don't skip any of those things. This is a bare minimum result here. Yes, I skipped the H on the top because I don't need it. But you better show me the lone pair and the anion. And the lone pair attacks the carbon that has the halogen in the next step. This is the synthesis step. Attack the carbon with the halogen leaves, and end of story for this first reaction. I must have a dead spot on my screen. I can't write on it. I don't know why. There we go. Do it again. KH grabs a proton. Lone pair, anion, grabs proton. There's only one proton left. You're going to make an anion here. Got a butyl. New bond to a butyl. And we got an anion on top. There we go. Lone pair is a nucleophile.
Does BU stand for butyl?
Yes. Somebody asked, does BU stand for butyl? And the answer is yes. And seeing as this had 1, 2, 3, 4 carbons in a row, yep, that would be a good indicator that was a good answer.
So could we have written
You could have written BU and continue to do so, as I will on this the same question from now on. I just wanted to make sure you knew BU was for butyl. All right, so we got a C minus. Now what's going on here? Where it looks like we're putting a D, which is the same as a proton. It's a deuterium. So we're taking a proton off and replacing it with a different proton. That's all we did. Acid base to get here, acid base to get here. Acid base. I could even ask you for pKeq. I didn't. I could have. This is a pKa of 16. That's a reactant. Product pKa 25. 16 minus 25. Negative 11. And that's why this reaction works. All right. Now it's time for oxymercuration and protonolysis. That's what this combination gives you all the time. Let's do the mercury first. One arrow goes towards mercury, and that is the formation of the triangle that has partial bonds all the way around. Those two electrons end up as these partial bonds all the way around. 3 partial bonds. Mercury's in the top corner with a 1 plus. The other plus shared in the triangle. Syn addition to make triangles. Here's your boo. Triangles on one side is all I'm saying. You can't have half the triangle start on one side and the other half on the other. It just they don't meet. So that's why the D and the BU are on the same side. Now it's time to put an oxygen on there, on the more substituted carbon, because that's the one that stabilizes a plus charge better. That's this carbon. It's a carbon with two groups on it. This is a carbon with one group there and a D. D's an H, so that's not a group. Water. Water's your attacker. Water's your attacker. Here's the water. Lone pair. I need one lone pair. Comes at the more substituted carbon. Backside attack on your triangle. D bonded to purple. The butyl got pushed out. The water's here. And the mercury's up top with a real bond. Mercury's up top with a real bond. All of these partial electrons ended up in this real bond. And we don't have arrows to show how that happens, so don't even try. We do have an arrow to show how this bond happened, and we put it there. Clearly, we have a long way to go. This doesn't look like either of the products. So, what's next? Generally, if we generate an oxonium by attacking something with water, the next step is always acid base to get rid of the extra H. It's an oxonium, it's a strong acid. And your best base is sulfate ion. OSO3 minus. It's right at the top of the screen. If you don't believe me, I didn't invent it. It was already there. Acid-base reaction. Generates an alcohol attached to an alkene. I hope you know that's also known as an enol. It's not quite time to deal with the enol until we get rid of the mercury. Getting rid of the mercury is called protonolysis.
It's
H? Which one?
it's
Which H? Sulfuric acid's H. Provides carbon with a proton. Mercury just leaves as mercury 2 plus. It lost out on this bond. Carbon kept the electrons and made a bond, a sigma bond to hydrogen. And the deuterium is still there. And we still have the OH on here. On the more substituted carbon and a boo. And I'm really liking this second product, where the boo is attached to the carbon that has the O. We just have to show how to get there. How do we get to that? Oh, she nailed it. She said acid catalyzed tautomerization. The acid will provide a proton for the carbon here so that it becomes a CH2 with a D. That's a CH2 with a D right there. Right now it's a C with one H and a D. So the acid provides a proton for the pi to pick up. The base of that acid, the conjugate base of that acid, I'm going to draw it over on this side because the conjugate base of the acid has one job. Take the proton from the enol. The all right there. Take that proton. Always lead with the base arrow. And then the sigma here becomes pi. That's a carbonyl. The pi breaks and becomes a sigma to H. Sulfate ion is made. Sulfate ion was reacted. It's a catalyst. Sulfuric acid is used and then made, or we can think of it the opposite. Hydrogen sulfate is, I didn't draw hydrogen sulfate right there. I made my own unicorn today. Oh, tell me what's wrong with this so I don't lose a half point on my own test. The 3 goes with the O, not with the H. That's just a flat out unicorn there. Yeah. Okay. So you could say hydrogen sulfate was the catalyst and it was used and made. Or you can say sulfuric acid was the catalyst, it was used and made. I do prefer the second one, as the student correctly stated. That is the more reactive partner. So you should name it as an acid catalyzed tautomerization. I'd like to point out in the hydroboration reaction, there's a tautomerization as well. But in that one, the acid-base pair is hydroxide and water. Hydroxide is the more reactive of those species. So it's called base catalyzed tautomerization. You won't be asked for what it's called. The arrows are identical in both tautomerizations, with the base grabbing an H, the sigma between H and O becoming a pi between O and C, and the old pi picking up a proton to H. So just remember, tautomerization, the mechanism is always the same. So we're about halfway there. It's a big question. It's time for some labels, isn't it? What kind of labels are we going to come up with here? The usual. We got a big explanation ahead of us too. Circle the major product formed at the end of the sequence. Explain my choice. Well, the choice happened right here. That happened when we did this. So this is part of B. Backside attack. It's not about the backside attack. It's really about on the more substituted carbon gives Markovnikov. There you go. That's why we circled that product that had the O on the more substituted carbon. Don't pick the product where O is on the less substituted carbon. That's not this reaction. So once again, I want to make sure that you know it's really, this is the most important thing here. Backside attack just made this thing anti, but in the end, we don't care about anti or syn because it's freely rotating. There's no wedges or dashes here. Now it's time to get our Lubnu Habibi on. And you remember, the attackers are always Lubnus. So this is lately I've just been doing it this way all the time. Everything that starts an arrow off, put a Lubnu on that molecule. And then go from there. That's starting it off, Lubnu. Lubnus react with ELAs, always. Lubnus are the attackers. ELAs get attacked. Lubnus are the attackers. ELAs get attacked. Oh my goodness. You do it this way, the points come fast. Here's the attacker. Lube nu. Here's the attackee, the thing that gets attacked. Ila. Here's the attacker. Lube nu. Thing getting attacked. Ila. Here's the attacker. Here's the thing getting attacked. Here's the attacker. Here's the thing getting attacked. Tautomerization is cool. Here's an attacker. The thing that gets attacked, Ela. But this pair of pi electrons is an attacker on another molecule, and that's the thing getting attacked. 4 sets of labels for tautomerization. Well, there's 3 molecules involved. So that's an attacker, lubnu. Thing gets attacked, Ela. Move over to the right side. This thing's an attacker, it's a lubnu. When it attacks Zila, only labels left are, if you're attacking a proton, you're also Bronsted. So go look for all the reactions where a proton was getting attacked and put in BA and BB. We'll go hot pink. H minus attacked a proton. So that's an Ilaba that got attacked. Lubnu Habibi is the attacker. We do not put the BB, BA on these 2. This is a C getting attacked. It's a C. Here's an H getting attacked. Lubnu is also Habibi. Ela is providing a proton. It's an Ilaba. Same for DOD. D is a proton, by the way. And BB here. Do not add anything to these labels. You're attacking mercury. That's not a proton. Do not add anything to these labels. You're attacking a C. That's not a proton. That's a proton getting attacked. Ilaba, the attacker. Lubnu BB. And Lubnu BB. His labels are a little. Oh, wow. There we go. Oh, pen, pink, go. And we got Ilaba here. Oh, it's an eraser. Pen, pink, go. And the attacker, Lubnu BB. Ooh. It's tiring. Well worth it though. Big picture worth lots of points.
Wait, what about the right side? Isn't it a brush and base?
Oh yeah, I didn't even see those because the screen had too much going on, huh? Ilaba and Lubnu BB. Thank you. Oh, we didn't go hot pink on those, but forgive me. All right, so that provides an end to this excellent review opportunity. And that's that. And we'll see you on our next one.